When people think about memory performance, they often focus on latency. How long does it take to get data? But there's another equally important factor. How much data can you move per second? That is memory bandwidth. In this video, we're going to explain what memory bandwidth is, how it differs from latency, how it affects real-world software performance, and why high-performance systems are often limited by bandwidth rather than compute speed. Let's begin with a simple definition. Memory bandwidth is the amount of data that can be transferred between memory and the CPU per unit of time. It's usually measured in gigabytes per second. If latency is the delay before data starts arriving, bandwidth is the rate at which data flows once it starts. Imagine turning on a tap. Latency is how long it takes for water to start flowing after you open it. Bandwidth is how much water flows per second once it's running. You can have low latency but low bandwidth. You can have high bandwidth but high latency. They are different properties. Now let's connect this to software execution. Modern CPUs can process massive amounts of data per second. SIMD units can operate on multiple values per instruction. Superscalar cores can issue multiple instructions per cycle. But all of that compute power requires data. If the memory system cannot supply data fast enough, execution units will stall. Even if latency is acceptable, limited bandwidth can become the bottleneck. This is especially true in workloads that process large datasets. For example, video processing, machine learning, scientific simulations, database scans. In these cases, the CPU may stream large amounts of data from memory continuously. If memory bandwidth is insufficient, performance plateaus. Now let's talk about how bandwidth is determined. Several factors influence memory bandwidth. The width of the memory bus, the memory clock speed, the number of memory channels, the memory technology itself. For example, dual-channel memory can roughly double theoretical bandwidth compared to single-channel configurations. High-bandwidth memory technologies increase transfer rates by widening the interface and increasing frequency. But theoretical bandwidth is not the same as sustained bandwidth. Real programs rarely achieve maximum theoretical numbers. Why? Because bandwidth depends on access patterns. Sequential memory access is efficient. The CPU can stream data in large chunks. Prefetches can anticipate future requests. Cache lines are fully utilized. Random memory access is inefficient. Cache lines may only partially be used. Prefetches may fail. Memory requests may be scattered. This reduces effective bandwidth. Now, let's connect bandwidth to cache lines. When the CPU loads data from memory, it transfers an entire cache line. If you use only a small part of that cache line, you're wasting bandwidth. This is called poor spatial locality. If your program repeatedly accesses large structures but uses only small fields, you may saturate memory bandwidth without doing much useful work. Data layout matters. Now let's discuss bandwidth versus compute balance. In many high-performance systems, there is a concept called the roofline model. It visualizes performance as limited either by compute throughput or memory bandwidth. If your program performs few computations per byte of data moved, it is bandwidth bound. If it performs many computations per byte, it may be compute bound. Understanding where your program sits on that spectrum determines how to optimize it. If it's bandwidth bound, improving algorithms alone may not help. You may need to reduce memory traffic, compress data, improve locality, increase arithmetic intensity. Now let's address memory-level parallelism again. Modern CPUs can issue multiple memory requests simultaneously. This helps utilize available bandwidth more effectively. If only one memory request is active at a time, bandwidth may be underutilized. Parallel memory operations increase throughput, but they must be independent. Just like with latency hiding, structure matters. Now let's connect bandwidth to multi-core systems. In multi-core processors, cores often share memory bandwidth. If several cores are streaming large datasets simultaneously, they compete for the same memory resources. Even if each core individually is efficient, total system bandwidth can become saturated. This is why scaling performance across cores is sometimes limited by memory bandwidth rather than compute. Adding more cores does not increase memory bandwidth proportionally in many systems. Now let's compare bandwidth across memory levels. L1 cache has extremely high bandwidth. Data moves from L1 to registers very quickly. L2 and L3 also provide high bandwidth compared to main memory. Main memory bandwidth is much lower relative to CPU execution capability. This is another reason why cache-friendly code performs better. By keeping data in higher cache levels, you increase effective bandwidth. Now let's discuss streaming workloads. In streaming workloads, large arrays are processed sequentially. These often become bandwidth-bound. Even if each operation is simple, the sheer volume of data movement dominates performance. This is common in image processing, video encoding, and numerical simulations. In these cases, improving memory bandwidth through better memory configuration or data layout can have a larger impact than improving CPU frequency. Now let's zoom out and connect everything in the series. Instruction dispatch selects work. Branch prediction maintains flow. Pipelines overlap execution. Out-of-order execution hides latency. Superscalar issues multiple instructions. SIMD processes multiple data elements. Caches reduce latency. Memory latency defines how long you wait. Memory bandwidth defines how much you can move per second. Together, latency and bandwidth define the performance limits of the memory system. Understanding both is essential for understanding modern software execution. If your program feels slower than expected, the bottleneck might not be computation. It might be memory movement, and memory movement is governed by bandwidth. If you want to continue deeper into the memory system, the next step could be exploring memory-level parallelism in detail, cache coherence in multi-core systems, or the roofline model more formally. But for now, you can summarize memory bandwidth like this. Memory bandwidth is the rate at which data can be transferred between memory and the CPU. And in data-heavy workloads, it often defines the upper limit of performance. Understanding that principle changes how you think about optimization. It shifts the focus from just computing faster to moving data smarter. And that is a crucial step in mastering software execution.